Alright, today we're going to talk about Clojure Functions. So a function is a named block of code that can take some parameters, and in Clojure, functions always return a value. Now the value of the last statement inside the function is implicitly or automatically returned from the function. And this was also true in Ruby. There is no return keyword in Clojure. It's just the last statement inside the function that automatically gets returned. You can create a function using the fn function. So this would be the syntax on how you would call a function. Fn is the name of a function. This is saying we want to create a new function that has some parameters. Notice the parameters are in a vector, so we have the square brackets. And then we have some body. Okay. So let's look at a real example. Okay, so here we have a function that takes a name, that's the parameter, and then inside the body what we're doing is we're calling the function called printLine, which does exactly what it sounds like. It prints something on a line, and then what we're going to print is the name. So printLine takes a group of parameters. All the parameters will be printed on their own line. If I were to run this though, you'd see that, well, first of all, I didn't call the function, right? So that's an issue. How do we call this function? Well, we have a problem now because it doesn't have a name, so there is no way to call it. Let's go down here. This is basically exactly the same code that's highlighted here. So this is a function. That's what the fn function does. It creates a new function for you. If we want to call it, remember the rules in Clojure is we have to put it in a list. We have to put a function as the first parameter in a list, or the first item in a list. And it will automatically be called. So now we should see my name printed. Right? Okay. So we had a list with two things on it. This function and this string. Okay, but this is kind of inconvenient to build a function like this. Every time you wanted to call the function, you'd have to basically copy and paste it. So it would be much better if we could give this function a name, right? And that's exactly what the def function does, right? It creates a binding. This is saying there's going to be this thing called printName, and what it is a reference to this function that we've built. Okay. Now we can call the function anytime we'd like just by putting it as the first element in a list. And we could reuse the function over and over again. Right? We don't have to keep redefining this function. We just call printName again and again. Okay, we could also use there's a slightly shorter syntax that creates a name and the function together without using the def. Okay, so that's the defn function. So syntax-wise, we have defn, that's the name of the function, and we can give a function name, a parameter list, and then the body of a function, all within this outer set of parentheses. Okay, so here I'm going to do a different version of printName. Okay, here's the parameter list, here's the body. It's just going to again print the name out, and this works exactly the same way. Okay, so I prefer this defn style. I think that's nice and short. You can also overload functions. So a function overload is the same function name with different parameter lists. Okay, and we do this by providing multiple parameter list and body pairs inside a defn. Okay, so here I have a function called hello, and there's two implementations. The first one, you notice it has a parameter list that takes exactly one parameter. And what do we do inside here? We print hello and the name. So str, remember, is the Clojure function to concatenate a bunch of strings together. So this will take the name and hello and squeeze them together and then print it out on a line. There's another version, another implementation that has an empty parameter list. Okay, and What do we do in that case? Well, we're calling the exact same function hello. This is a recursive call, actually. And we're passing in a string for the name, which is just going to be the word stranger. So this version calls this implementation. This one calls this one. Okay, like Ruby, you can define a function that has a final parameter that collects extra parameters into a sequence. So let's take a look at that. Okay, so here we have a function called family count. Has 3 parameters: husband, wife, and kids. But notice this ampersand here. This basically says anything left in the parameter list after the first 2, in this case, wrap them up into a sequence called kids. Okay. Now what this function does is it calls println, it says family of, and then there's a function called count, which works on sequences, which will tell you how many items are in there. And then we're going to add 2 to that number for the husband and the wife. Okay, so when I run this, okay, with Mark, Laura, Buddy, and Patrick, that says it's a family of 4. Okay, if I add my cats in there, I have a cat named Willie and a cat named Juan Pablo. Okay. Now this tells us we have a family of 6. So again, what that ampersand means is when we call the function, we're going to match parameters. So husband to Mark, wife to Laura, and then everything after that point is going to be wrapped up into a sequence called kids, which we then count and add 2 to. Okay, let's talk a little bit about flow of control in Clojure. So there is a select statement, but it works a little bit different than in most imperative programming languages. So here's a function called ice or not, and it takes a temperature as a parameter. Okay, and here's our if-else statement in Clojure. So if is a function, and we always pass it, or the first parameter to that function is always a condition. So here I'm using the less than or equal to. This basically says, is temp less than or equal to 32? If it's true, this value will get returned from the function. If this is not true, then the second string here will get returned from the function. Okay, so with the values 40, 32, and 20, we get water, ice, and ice. Now Clojure's if only allows you to do one thing in each branch. Most of the time you'll call a function that returns one value in either branch. If you'd like to do more than one thing in a branch, you must use the do function. So do is like a block. The last value inside do is always returned. However, all but the last statement inside a do are side effects because their return values aren't being used. Now remember, a side effect is some part of a function that does not contribute to the return value. So let's look at an example. Okay, here we have a function called ice or not, which takes a temperature. We're calling the if function. We have this condition. Is the temperature less than or equal to 32? If so, we're going to return ice. But if that's not true, we're going to evaluate this, and this is going to return something from the function. So do is a function, and we could put as many statements as we'd like inside a do. Only the last one will get returned. So if the temperature happens to be greater than 32, well then what we're going to do is print this message, or perhaps we would actually start a freezer or something like that, and then return the value water. Okay, so I'm going to pass in 20 and 40. Let's see what we get. Okay. When we call ice or not and we pass in the value 20, 20 is less than or equal to 32, so the print line here is going to print ice. That's what we see here. And then when I call ice or not with the value 40, since 40 is not less than or equal to 32, this whole do is evaluated. And as a side effect, we print out the message to start the freezer, or we could actually, like I said, start some hardware to actually turn the freezer on. But then the last thing inside the do is just this string, and that's what gets returned from the function. Okay, multi-way branches are available with the condition function. And condition takes a group of conditions and bits of code to execute if one of those conditions is true. The first one that evaluates the true will be executed, and all the other ones will be skipped. Okay, so here's a function called getGrade, which takes a grade. Here's our condition function, and we have all these sequences of things that evaluate to true or false, followed by a value to return. Okay, so we have that for A, B, C, and D. Here we have a keyword else, and all keywords evaluate to true, so you could put any keyword you'd like in there. Else seems to be the most logical one, though. And if none of these are true, well then this one will always be true and will return that value there. So if we pass in the value 88, we get a grade of B. If we pass in a value of 68, we get a value of D. Okay, let's look at maybe another example. So this is another water state function here, where we have a condition. If the temp is less than or equal to 32, we do ice. If that's not true and the temp is less than 212, we must have water. If neither of those are true, then the water must be steam. In that case, we'll return steam. So we're calling this function with these three values. We should see steam, water, and ice. Let me show you another example. Okay, here's a function called largest of 3, which is going to look at 3 numbers, and it's going to use this condition to always return the largest of the 3. So the first one basically says we want to use the AND function. This is like a logical AND. So if num1 is greater than or equal to num2 and num1 is greater than or equal to num3, well then we know num1 of the 3 is the largest. And we do something similar for num2 and num3 here. And we'll see the output always returns the largest, which is 3. So I have every combination of 1, 2s, and 3s here. Okay, so condition, again, you pass it something that evaluates to true or false. And then right afterwards you have a value that's going to be returned from that condition. Okay, let's talk a little bit about looping. So there are helper functions to iterate through a sequence and apply some function to the items in that sequence. Most of the time you're going to use these little helper functions instead of writing a traditional loop. So the first function we'll take a look at is called filter. And filter takes another function that evaluates to true or false. And all the elements in the sequence are passed into it, and only those that return true are collected into a new sequence. Okay, so here we have a print. We're going to print out the odd numbers. So the important part of this one, though, is this code right here. So the function that we're calling is called filter, and the first parameter that we pass in is another function. This is the odd function that we saw earlier. Okay. Then we pass a sequence. This happens to be a vector of integers. And basically what's going to happen is each one of these values is going to be passed into the odd function. And if this function evaluates to true, we're going to collect that value. That's going to eventually be returned from the filter function. So 1 is odd, but 2 is not, 3 is odd, and 4 is not. Okay. What gets returned from the filter function should be a sequence with 1 and 3. And then when we do the print line, we should see only those values. Okay. So those are the odds. If I add a number 5 here, we should see one more odd. Okay, so filter is interesting. You pass it in another function, and it will evaluate each one of the values in the sequence and collect only the ones that return the value true. Now there's another function called map. Map also takes a function and applies it to all the elements, and it collects the results into a new sequence. So the only difference between filter and map is map doesn't care whether the function evaluates to true or not. It just applies the value to all the elements in the sequence and collects them in a new sequence. Okay, so here's the map function. We're going to pass in the inc function. Remember that increments a number by 1. So this basically says the second parameter here is a sequence of integers. So we want to map each one of these values. We want to pass in to the function called inc, and it's going to collect all of the results. Okay, and that's what the map function returns, is that new collection of all those values. So we should see the numbers 1 through 4 being returned. Right? That's because we passed in each one of the numbers 0 through 3 to the inc function, collected those return values, and eventually printed that to the screen. You can also pass in more than one collection to the function, and what we're going to do is apply the function to pairs of elements. Okay, so here's an interesting one. We're going to call map, and the function that we're going to pass into map is the multiplication function. Okay, but now instead of passing one sequence, we're actually passing 2 sequences. And what's going to happen is it's going to take a value from each sequence, and it's going to call the multiplication function. It's going to pass in the value 0 and 100. Then it's going to take 1 and 200, then 2 and 300, and so on. It's going to collect all those results, and it's going to be returned so that we can print out 0, 200, 600, and 1200. Okay, reduce is a function that takes a function and applies it to the first 2 elements in a sequence. It then collects the result of that operation and applies it to the next value in the sequence, and so on. So if you wanted to sum up all the values in a sequence, you would use reduce. Okay, so here's the reduce function. We're going to pass in the addition function and this list of the numbers 1 through 5. So I'm quoting that so the evaluator doesn't try and treat the number 1 like a function. Okay, so it's going to apply the plus function to the first 2 elements. 1 plus 2 is 3. It's going to take that result and add it to, or apply it to the third item. Then it's going to take that result and apply the function to the 4th item, and so on. So this should give us the sum of the first 5 numbers. We do a very similar thing here with the multiplication function. So 1 times 2 is 2. We're going to take that result and multiply it by 3 to get 6. Take that result, multiply it by 4 to get 24, and so on. And then reduce, again, we're passing in the concatenation function string. And again, it's just going to apply that to the first 2 values, take the result, and apply it to the third. Okay, and we get the sum of those values is 15. The product is 120. And when we concatenate all these values together, we get 1, 2, 3, 4, 5. Okay, with map, filter, and reduce, you can do an amazing amount of things without having to write a single dreaded for int I equal to 0 while I is less than whatever. Okay, you might find it odd that there is not even a while or a for type loop. Now there is a for form that allows you to use every permutation of a set of values in a sequence in an expression that returns a sequence of the results. So let me show you how that works. Okay, so here I'm defining this thing called result. I'm not creating a function here. This is just I'm giving the name. I'm binding a value to this name called result. The interesting part is what I'm doing with the for function. So for has these things called bindings. Okay, so this is basically like saying we want a local variable called a, which holds the values 1 and 2, and a variable called b, which holds the values 10 and 100, and so on. So those are the bindings. Then what we can do with those values, a, b, and c, is collect the result of applying some operation to them. So in this case, we're going to multiply. And again, we're going to use every single permutation. So we'll do something like a will hold 1 at first, then b will hold 10, and then c will hold -1. We'll multiply all those together and collect that result. Then we'll do a will be 1, b will be 10, c will be +1. Okay, and then we'll move on here and we'll say a is 1, b is 100, c is -1. So we're going to hit every single one of the permutations, collect the result of applying this operation, and we're going to store that result inside the symbol called result. Okay, and you see we get -10, 10, -100, 100, -20, 20, -200, 200. And if you trace these out, what you'll see is the last element changes most frequently, and then the middle element changes less frequently, and the first element changes the least frequently. Okay, so here are a few more examples using for. Okay, again, we're going to create the symbol called result, and we're going to use for. This time we only have a single collection. This is actually this is a binding. We're going to have this binding called word, and it's going to hold each one of the strings inside the sequence here. And we're going to call the format function, which is basically going to replace this %s with the value of word. That's what the format function does. And then we're going to collect those results and print them. So this is how we might generate some HTML or something like that. So the quick brown fox. Okay, for always collects the results, and we can have one binding or two bindings or 20 bindings if we want, and we'll get every single permutation of them. Here's another example. This one's called nums in range. We have a for, we have a binding called num, and we're going to find out shortly there's a function called range which will produce a sequence between in this case 10 and 14, or 1 minus that last parameter. So num is going to hold each one of those values individually. We're going to apply num to the body portion of the for. So we're going to basically add 10 to each one of those values, collect the results, and those results are going to be stored inside this thing called nums in range, which we then print. So this should give us the numbers 20 through 24. Okay, you can also add some filtering with the when and while keywords. So let me show you an example of that. So here we're going to store the results. We have a for. N is the binding, so n is going to hold each one of these values in turn. Okay, but only when n is even. Okay, so you use the when keyword here, and you pass it a function that will evaluate each one of the values inside the sequence, and only when that evaluates to true will we actually collect that value. So here I'm not doing anything really special with the value. I could have done some arithmetic or something else. Here I'm just going to collect. I want to collect basically the even values. Okay, and that's in fact what we've done here. Okay, we just collected those that evaluated to true. Okay, let me show you another example. Okay, here I am creating a function called perms for permutations. It takes no parameters, but we do have this for form in here. So fors have these bindings, inner, middle, and outer. You could kind of think of these as being a nested for loop, where this is the innermost loop. The values 3, 4, and 5 are going to be iterated over the most frequently. And then this would be the middle loop, and this is the outer loop. Okay, so here we have another when. So we're going to we're going to multiply the values of outer, middle, and inner together, and only if the result is odd do we actually care about that combination or that permutation. And what do? Well, we're going to create this series of strings. Okay, so it's going to collect these strings where I'm concatenating each one of the values and showing the result of multiplying them all together. So that's a function, so in order to call it, I have to wrap it inside a set of parentheses. And we should see all of these products are in fact odd. Okay, because I specifically asked to see only the odd ones. Okay, there aren't really local variables like the ones we have in most imperative languages in Clojure, but we do have this form called let. Let allows you to create bindings for values that will be used inside of a function. Okay, this helps by storing intermediate results and giving them a name that can be used in the rest of the function. Okay, so here's a function that takes no parameters. Let, okay, allows you to create some bindings. So again, you can think of a let as it's kind of like how you create local variables. We're saying this name is going to be bound to this value. Okay, and then we're going to have this the body that can use those variables. Okay, this isn't executable code. Let me show you an example that does run. Okay, so here we have a function called printStudent. Takes a first, middle, last, and GPA for parameters. Okay, then I have a let, and again, the let is this series of bindings. So I want to have this local variable basically called full name, and I want it to be bound to the result of concatenating the last name, comma, the first name, and then the first letter of the middle name, followed by a period. All of those are going to be evaluated, squished together, and full name is going to refer to that. Okay. Then what I want to do inside the let, so the let starts here and ends here. So full name has a certain scope, a certain time when it's available. That's only within the let. And what I want to do is print out the full name. Okay, and then the let will end, and we'll just go on with the next statement inside the function, which will print out the GPA. Okay, so we see the name in this format. Okay, all of that was accomplished by creating this let and storing the result of that conversion of the names into a single string. The scope of the let bindings are within the let function call itself. Parameters to a function are bound to names by default. We don't have to, for parameters, we don't have to do a let. But that's basically what these are. These are names for these things here in the function call. Okay, and they're bound automatically. The scope of parameter bindings are the entire function. Okay, let allows you to store intermediate return values to be used in a chain of function calls to come. So the arrow operator in Clojure similarly passes values through a pipeline of functions without naming the intermediate results. Okay, so this is actually not too different from the let operation, although it's going to look a little funny. Okay, so this is not quite executable code, but let's look at this code. This is C-like or Java-like code. So we have a function, and this function 1 takes 3 arguments. First argument, second argument, third argument. When we call this function, it's going to return a value which we're storing in x. Okay, and then what we might want to do is take that return value and pass it as the first parameter to another function, func2. And func2 might take 2 parameters, so here's the second argument. Okay, we're going to take that result and maybe pass it into a third one. So we have this kind of chain of function calls that we want to take the previous function call's value and we want to stick it in the parameter list for the next function call. We do that in Clojure with this arrow operator. Okay, so this is actually a function. And the way it works is, it's a little odd, but you take the first argument, the function 1's first argument, and that comes right after the arrow. And what we're saying here is we want to call func1. This is going to be placed, though, in this position. Okay, it's always going to be the first argument in the function call. Then we still have the second argument and the third argument. Okay, the result of calling this whole function is going to be stuck in this position. Right, so func2, this is kind of like we stored the value x, and now we're passing it as the first element in the next function call. Okay, and then we have the second argument. The result of calling this function is automatically going to be passed into the third function, okay, and so on. So let's look at some real code here. Okay, so we have this, what looks like a really odd group of code here. But what eventually happened is we printed the value 13. Okay, so let's pick this apart a little. Okay, we had the arrow, plus 1, 2, star 3, plus 4. Okay, you can think of this as, again, the thing that comes right after the arrow is going to be fed into the next function call as the first parameter. So you could think of this as evaluating this and sticking it in here. So 1 plus 2 is 3. It's kind of like we're putting a 3 here. 3 times 3 is 9. Then we're going to take that result 9 and stick it inside here, right, as the first argument of this next one. And 9 plus 4 is 13. That's how we got the value 13. Okay, so another way to think about that is, again, that the thing that comes right after the arrow gets plugged in as the first parameter to the function call. And the result of that gets plugged into the second function call. Right. So this got placed there, and then the result of calling that function got placed there, and that's how we got the final value of 13. Okay, we can simulate object orientation in Clojure. So earlier in class we simulated object orientation in C by creating a structure with a list of data members and a list of methods. We had some supporting methods to help us manipulate things. We had call function, read data, etc. Now, functional programming is not the same as object-oriented programming, but if we really wanted to, we could do something similar. We could simulate it. One way to represent an object would be to create a map of data and then provide some methods that worked on that map. So we can think of a constructor as a function that returns a map with the correctly filled in data members. Okay, so let's take a look at this. Okay, so I have this function called point. Point takes two parameters, x and y. Remember how functions work. The last statement inside the function automatically gets returned from the function. Okay, so what this is saying is when somebody calls the point function, we're going to create a map. I know this is a map because of the curly braces. There's going to be a key with x and y, and this x and this y are actually going to get filled in with the parameters. Okay, so here's where I'm calling point. Point is kind of like a constructor. I'm passing in the values 2 and 3, and now P is going to hold a map that has these key and value pairs, x and y. So remember how maps work. If you pass in a keyword to a function call and a map as a second parameter, it will go and look for the value associated with this key. Okay. So I should see 2 and 3 printed to the screen here. Okay, well, if we wanted to, for example, not allow negative values in the point map, we could alter the constructor. Okay, so here's a very similar one. Point takes an x and a y. It's still going to create this map, but it first checks to see is x less than or equal to 0. If that's true, we'll just set the x member to 0. If it's false, we'll set the x member to what gets passed in. We'll do something similar for y. And now when we create a point, we're saying -2, 3, but the -2, since it's negative, will get turned into a 0. And if we did it like this, now we should see 2, 0. Okay, we can add getters and setters. Okay, so here's the constructor that just returns a map. Here we're creating the point 2, 3. Here's our getters and setters. We have one called getX, which takes a point, and then we simply pull out the x member for that point. Okay, here's another function called getY that takes a point, and we simply pull out the y member. Okay, so these are kind of like getters and setters. We're calling getX and passing in the point. We should get the correct values back, 2 and 3. Okay, we can include some other methods. Let's say we want to be able to shift a point. Again, we have the constructor, we have the getters, and we have this function called shift, which takes a point, an x increment, and a y increment. Okay, and basically what we want to do is we want to create a new point that has the old point's values plus these x and y increments. Okay, so the way this is going to work is we're going to use, this is basically the entire function, where we're going to call the point constructor. Right? That takes 2 parameters. This is the first parameter, where I'm basically calling the getter on this point, and then I'm adding to it the increment value. That should give us a new x. That'll be the first parameter to the point constructor. And I do something similar here for the y. Okay. I use the getter to get the y value, and I add the y increment. Okay, then down here I create a point called p. Then I call shift. I pass in p, 10, and 10. That's going to create a new point, which I call new p. And then I'm going to call the getters and setters for that value. I should see 12 and 13 for this new point. Okay, so this certainly isn't object-oriented programming in the traditional sense, but it does have a kind of a similar feel of collecting related data together, like we did with structs in C, and providing functions that work on these objects, kind of like methods in a class. In fact, this is one of the defining characteristics of functional programming. We avoid making explicit types or classes. Instead, we collect data and methods that only work on that data. Okay. We create more general maps and functions that accept maps. These functions don't really care about the types. They will accept any map that has the required data members. So for example, here's a new constructor, maybe point 3D, which takes x, y, and z, and now it creates a map with an x, y, and z member. So I'm creating a point 3D with these values, and now what I can do is I can reuse the old getX and getY. Remember, this was for a 2-dimensional point. There's no need for me to rewrite the setters. I haven't really created a new type. All I've done was reuse some functions that all the functions really required was that there was an x or a y member. That's what the getters required. Okay, this style is much more loose than strict. No one or no compiler is making sure that the things we pass around to functions are of the correct type. This is another example of duck typing. So if it walks like a duck and it talks like a duck, well then it's a duck. This makes it a lot easier to change where data lives than in traditional classes. I've been mentioning that as a problem in something that I kind of find annoying in object-oriented programming languages is moving things around tends to be very difficult because you can basically break the interface to a class. An object-oriented constructor, for example, assumes you're creating an object for any legitimate use. As such, the constructor must fill in all the values for the instance variables. The nice thing about using maps is that you can write test code that just has the bare minimum data members that a function needs. Okay? and one can make the simplest object required just for some test case. A lot of tests in object-oriented programs, you write a bunch of extra code just to set up the object to make it a valid object, when you're not even going to use most of the data that's associated with that. Okay, so this functional style says that we're going to use maps and functions instead of strictly defined types or classes. And we're going to have functions that take as parameter other functions, okay, or maybe even return other functions. And then finally, the data is going to flow through functions by kind of abstracting away the flow of control. Okay, and that's our introduction to functions. Okay, next we're going to talk about using more Java functionality inside Clojure.